Hello, everybody. Welcome to Intelligence Maxing Day 62. Alright, I got some exams coming up tomorrow, so gonna try to speed run through some flashcards, especially my 402 and 472 class. So let's get to it. Alright, show that when the CAPM holds in equilibrium, all traders' optimal portfolio is perfectly correlated with the market portfolio, regardless of their risk tolerance. Okay, so there's a few things to break down here. CAPM holding in equilibrium, that just means that usually all of the traders will hold a market portfolio, and they'll just vary their beta depending on their risk tolerance. So all traders' optimal portfolio is perfectly correlated with the market portfolio. Alright, so CAPM is a single factor model that says the returns of any asset or any portfolio is simply just the risk-free rate plus the beta of that asset times the market risk premium. And in this case, we're kind of just trying to see or show that the optimal portfolio is perfectly correlated with the market portfolio, and regardless of the risk tolerance. So in order to do that, we need to show that the correlation between the two portfolios are equal to 1. And I think the way we could do that is, so the CAPM optimal portfolio is just beta times the excess returns on the market, and then the market portfolio, I guess we can think of just as the excess returns of the market. So we need to find the correlation between beta, we'll call it RM, and then just RM. And I believe correlation is the covariance of the two variables, and we divide it by the standard deviation, the product of the standard deviation, so the two variables. So we'll have something that looks like the covariance of beta RI or RM divided by the standard deviation of beta RM times the standard deviation of RM. Okay, so covariance is linear, so I believe we can bring out the beta term, so it'll be beta times covariance of RM. That just becomes the variance of the market. And for the standard deviation, it's not linear. So if we bring out the beta from so standard deviation is the square root of variance of beta times RM. And if we bring out the constant beta from the variance, then we have to square it. So it becomes beta squared variance of the market. And then we take the square root of that. So that just becomes the square root of beta squared, which is just beta times the square root of variance. We multiply that by the square root of the variance of the market, which becomes the square root, which just becomes the variance of the market actually. So our final form will have beta times the variance of the market divided by beta times the variance of the market. That just is equal to 0. Alright, so this is our formula for correlation. Covariance of x and y divided by the standard deviation of x and y. So if the CAPM holds, all traders will hold the optimal portfolio, but their allocation to the market portfolio will depend on beta, right? Okay. And so we can show that this is how you can express the correlation between the two, and this is how we derived the denominator here. So this is what I was talking about, how standard deviation is just the square root of variance, and if we bring the beta or the constant outside of the variance, we need to square it. We can just distribute the square root, and then this will just leave us the beta times square root, beta times standard deviation of RM. Then we just multiply those two. So this is standard deviation squared, and that just becomes your variance. Alright. Evaluate the following statement true or false. The NASDAQ index is a good empirical proxy to represent the market portfolio when running a capital asset model regression. If so, explain the reason why. If not, explain why not. So I think this is probably false, just because the NASDAQ index is not a good empirical empirical proxy. So NASDAQ is kind of overweight tech and biotech, maybe even communication stocks. And so it doesn't really represent the entire stock market, maybe compared to something like the S&P 500. The theory of the capital asset pricing model states that firm characteristics other than its beta should not affect its expected return. If so, explain the reason why. If not, explain why not. So I think this is true. The CAPM is a single factor model. All of the returns of an asset should depend on its beta, which is its sensitivity to market returns. Okay. How does funding liquidity and market liquidity interact? So it seems like funding liquidity is sometimes caused by market liquidity. So market liquidity refers to the idea of high transaction cost. And so if you have high transaction costs, that usually means a high bid-ask spread, which further means that there's probably not a lot of securities being bought and sold. And that can cause funding liquidity in the sense that there's not enough securities going around to short. There's not a lot of people willing to lend you the securities, maybe because they think it's going to be high transaction costs, they're losing out on some bid-ask spread. Or it could be that no one is willing to lend to these customers because those securities are super thinly traded, so there's a lot of risk involved. So yeah, this is why I feel like, yeah, it's okay. Let's leave this now. So see the following results from the CAPM regression of 5 portfolios. Betas, what are the evidence for/against the CAPM? Betas move opposite direction to expected returns. Alphas are consistently non-zero, assuming those alphas are jointly statistically significant. So it seems like all of these, I'm not entirely sure what jointly statistically significant means. So I want to see actually. Also, Chat GPT 4.0 for Omni came out. Seems like big deal. Mayhaps. Let's go BUFN. Okay, so what does jointly statistically significant mean? It looks like I'm just texting someone. Can I not do 4.0? When variables are said to be joint, it means that their combined effect in the model significantly affects the dependent variable, even if some or all of them might not show strong statistical significance. Okay. Okay, so pretty much it just seems like maybe some of these alphas are not individually significant in, let's say, the different quintiles, or quartiles, but it seems like that if you were to kind of look at this as a whole, the alphas are pretty significant. And so in that case, both of these are evidence against the capital asset pricing model. First, betas move in opposite directions to expected returns. Usually they should be linear and follow the same direction. So you would expect the betas to also rise as the average return rises. And then alphas are consistently non-zero. Usually with the capital asset pricing model, there should not be an alpha that exists. Okay, therefore not all returns are explained by the assets beta. Okay. How is standard deviation from standard error? Okay, so apparently standard deviation is a measure of how spread out the data is from the mean, but the standard error is actually commonly used for estimators, and the estimators, or what standard error represents, is how spread out the values of those estimators are from sample to sample. So I think a good example here that StatQuest gave was the estimator for sample mean. So the sample mean estimator for the population mean. Right, you don't know the actual population mean of your distribution, of your data distribution, but you do know the sample mean. Or you don't. Let me backtrack here. So you have a population distribution. You don't know its population mean, but you do have some samples from that population. So you could maybe sample, let's say, 10, 15 different, 10 to 15 different people or things from your population, calculated sample mean. So you have one estimator, then you do another 15 people, then another 15 people, then another 15 people. So you take all of these samples, calculate the sample mean, and then you can kind of take a mean of means, in a sense, use that to kind of estimate the population mean. But I think what the standard error here represents is how much your mean will tend to fluctuate as you keep on sampling over time. Yeah. And I feel like it's mean divided by, the sample mean divided by the square root of the number of samples, but I'm not entirely sure what that means really mathematically. So consider the following single variable regression. Alright, assume that the errors are distributed independently and identically on a normal distribution of 0 and sigma squared, and show that the estimator beta hat 1 is also normally distributed given the observed xi. Okay. So we can show here that I believe, so the epsilon I is normal, and this can be the exact same as y minus beta 1, x1, and then beta 0. So I think there's a property with normal distributions where if you were to add two normal distributions, that becomes a normal distribution. And in this case, we're taking y here, we're adding y, and we're subtracting beta 1 x1 plus beta 0. So we're subtracting these two terms, and that's kind of the same thing as adding the negative of these two terms. So we are still really, we're still using two, I guess we can say by that property of a normal distribution plus a normal distribution is equal to a normal distribution. That means yi has to be normal, and that means beta 1 x1 plus beta 0 also has to be normal. Beta 0 has to be normal. I think that's kind of obvious here because we're summing up beta 0 plus beta 1 x1, but how do we know that beta 1 is normal? And so I think then what we could show is that beta 1 is exactly equal to, I think it's the covariance of x1 or xi and yi. divided by the variance of xi. So our independent variable here. And if we were to restructure that, it actually becomes the sum of x minus x bar times yi over the variance is it the variance or the sum of square residuals? I think it's the variance. Let me think about this here. So how do we get beta, right, in this? It is x transpose x inverse I want to say it's the covariance over the variance. I'll say that for now. And if we do that, that means, okay, it is the covariance over the variance, because the sum of square residuals, that we take the sum of square residuals and then we divide that by n, or n minus 1. So we do that. Oh, okay. So we could also take the sum on top of xi minus x bar, and the bottom will be sum of xi minus x bar squared. But we don't care about the n minus 1 or n because it cancels out, because we have the covariance on top and the variance on the bottom. So if we divide by n on the top and bottom, it just cancels out. If we divide by n minus 1 on the top and bottom, that also just cancels out. So we're just left with the summations here. And if that's the case, we could show that beta 1 is just the sum of, I think, c. So we'll say c is the ratio of x minus x bar over x minus x bar squared. And then we multiply that by xi. And so we know xi is fixed here, but we don't know what beta 1 is. But since we're adding all of these beta 1 xi's together, then that means we're just adding a bunch of normal distributions together. We have to. That's the property of the normal distribution. So I think that's how we can show it. So just to summarize, we rearranged our equation so that now it's expressed in terms of epsilon. So epsilon is equal to yi minus parentheses beta 0 plus beta 1 x1 xi. So what we're doing is we're kind of adding up or subtracting a bunch of variables, and if we were to add or subtract a collection of variables to get to a normal distribution, that means that those underlying variables have to be normal as well. And so yi is normal, and we can also show that beta 1 is normal by breaking it down to the covariance over the variance, and then we show that the top, the covariance, really can just be expressed as the sum of x minus x bar times yi, and then we divide that by the variance of xi, which is just the sum of x minus x bar squared. We can set that equal to c, and we multiply that by yi. And so we're multiplying xi, which is fixed, and then yi, which is normally distributed. So we're just adding up a bunch of normal distributions, and that is our beta I, our beta 1 hat. right? So we can represent this in a different form as beta 1 hat is equal to sum of ci yi, where ci is equal to, so this is the xi minus x bar, sum of square residuals. Now, in this case, we can see that beta 1 is the sum of normally distributed variables, which is normal. Okay. So see the following results from the CAPM regression. Yeah, I think we saw this before, but this is actually both against the CAPM. Betas move in opposite directions, so they should be moving the same direction. And alphas should be consistently 0. Okay, so we have to show that xi minus x bar times yi minus y bar is equal to the sum of xi times yi minus y bar. So this is kind of explaining the steps in the last problem, where we kind of went from the covariance over the variance to this weird summation thing. And this is kind of showing and breaking that relationship down. But I think big idea here is, okay, this we can kind of distribute out. So we have xi minus x bar times yi minus y bar. We could actually just multiply xi times yi minus y bar, and then we subtract x bar times yi minus y bar. So now we have two different, I guess, terms, and we can split up the summation. So we have sum of xi times yi minus y bar minus the sum of x bar times y minus y bar. Alright, so you notice that this is our left-hand sum, so that means our right hand, or our right term, has to equal to 0. And in this case, our right sum, so remember it's x bar times yi minus y bar. The x bar relative to the summation here is constant, meaning that for whatever I that we have, from 1 all the way to the number of examples, the sample mean doesn't change once we've actually calculated the sample. The sample mean doesn't change for each observation of the sample. It's exactly the same, unless you completely resample again, but that's not what the problem here is showing. This is after we've collected our sample, we iterate through all of the samples, and for all those iterations, the sample mean is the same. So we can just bring that out, it's a constant. And then now we're just left with the sum of yi minus y bar from I is equal to 1 all the way to n. And then again, you can kind of distribute the sum, so we have the sum of I equal 1 to n of yi minus the sum of I equal 1 to n of y bar. So you'll notice again that the y bar here is a constant with respect to the sum, so you can bring it out, and now you just have 1, the sum of 1 to n, which is just n. So you have y bar times n. And you have the sum of 1 to n of yi minus n times y bar. So if you remember how the sample mean is calculated, all it is, you take up all of the y's, and then you just sum all of them together to get this single value, and you just divide it by the number of examples. So that's exactly what we're doing here, but in reverse. So we're multiplying the sample mean by n, so that means we're just left with the sum of all the y's. And in that case, this cancels out, so it's just left with 0. So we're just left with this left term here, xi times y minus y bar. Let's go! Right, so this is what I mean by we can distribute the terms and then distribute the sums. We bring it out because it's a constant, and then this becomes 0. Right, so this is a quick derivation to show that's 0. We can further distribute the sums here. This becomes ny bar, and then once we take this difference, we'll show that ny bar is actually equal to the sum of yi, which is equal to 0. And once we plug in 0, this just removes this term and we get this final summation here. So this is where I kind of go into the details of x bar. It does vary statistically, so every single time you make a new sample or regression, it changes, but it's constant relative to the summation because it does not change for different observations within the sample. Let's go! Let's go! Okay, this one though is really hard. I don't even think I got it. So let's see. 25 minutes. I don't know if I'll be able to get this one, but let's see. So suppose that y is distributed normally with mean 0, variance of sigma squared, known variance sigma. You don't know the value of mu, but you have access to a random independent sample. So, oh wait, let me see. Are the parameters for the normal normally actually expressed as variances or standard deviations? Yeah, let's see. Okay, but you don't know the value of mu, but you have access to a random independent sample of size n from the same population, okay? So let y bar denote the sample, meaning from this random sample. You predict the value of the out of sample y using y bar. Show that the prediction error y minus y bar has a mean 0 and that y and y bar are uncorrelated. Alright, oof. Yeah, I think I got stuck on this one, especially on the uncorrelated part. Let's see, so it's variance. So sigma squared, so variance. But basically, you can show that the prediction error is y minus y bar pretty easily, has a mean of 0. So we can just take the expectation of this. So the expectation is linear, so we could just do the expectation of y minus the expectation of y bar. So that becomes mu, this becomes mu, so mu minus mu is equal to 0. Alright, so y and y bar, how do you show that they're uncorrelated though? This is a bit complicated, so we need to show that the correlation between these, or the covariance, is equal to 0. The covariance of of y and y bar is equal to 0. I want to say like it's just given because there's a random independent sample, so you're just sampling y independent a number of times, completely independent from each other, so sample mean isn't correlated, but I don't know how to show that mathematically. And it doesn't really make sense because I would think that the values of y somehow Alright, well, you could do the expectation of y minus the expectation of y times the expectation of times y bar minus the expectation of y bar. So that's the covariance. So you just take the sum of that. Ooh, maybe we can show that this is also... I'm gonna bring out a pen and paper, because like doing it in my head is kind of hard. But we might be able to show by using the properties of the covariance. So we have covariance of x, or let's do y bar, the expectation of y minus expectation of y times y bar minus expectation of y bar, which is equal to the sum of n is equal to 1 of y minus mu times y bar minus mu. Okay. So it seems like the one thing that does not change here is yi. And mu shouldn't change either, so I think we could just bring this out. So y bar minus mu, and then sum of n I is equal to 1. So this just becomes then y bar minus mu times the sum 1 of yi minus n times mu . So it doesn't seem like it's going anywhere here. Minus y mu, y bar mu plus mu squared. This also is not going anywhere. So we sum y bar minus sum minus mu times sum of yi minus ny bar u plus nu squared. Sample mean from this random sample. Divide this by n. This by n, so this becomes y bar squared minus u y bar minus y bar u plus u squared. Oof, yeah. Getting kind of stuck here. I have a problem. I have a feeling that I might get stuck a lot tomorrow. So I'm going to need to figure out what's the best plan of attack in order to not get stuck. So what if I do then? So plus expectation of yiu plus expectation of u squared. So expectation of yi minus y bar, y bar. I would assume it's u squared. We have u squared minus u squared minus u squared plus u squared. Alright, let's see. Let us see. So we have, oh man, expectation of y. This is hard. Wrapping this over here. yi times bar. Ooh, so yi, where n is the expectation of yi times expectation of yi times bar. And yi times How to show that yi random variable and sample mean are uncorrelated. What if I just copy and paste this? Guess it doesn't work. Let me see if I can find it. I don't want to take too much longer on this question, so I might think this is quiz 5. Yeah, I don't want to take too much longer, maybe 3 more minutes, and then I'll go. See what Omni's got. Covariance in terms of its expectations. So how do you get covariance of y y bar is equal to expectation of y minus let's try something. Oh man, okay, yeah, this is pretty complicated. Might just skip this for now. I'm pretty sure this is wrong here. Well, actually, these two cancel out. So we get, okay. God damn. Alright, so. Actually, do they cancel out? Yeah, so big thing here, I missed the plus sign. Oh my god. Oh my god. Okay, I'm gonna be honest, I kinda don't know what I changed to make this fail. I'm gonna add a plus here, right? Okay. Oh, yeah, could be it. Okay. Which is just equal to minus there we go. Yeah, where the hell did this thing go? Slash big. Alright, there we go. Yeah, makes more sense. Okay, so once we express this in here, then we get this complex expectation of yi, y bar. It gets pretty deep. I'm gonna just skip this for now. Say it's good. Okay, so consider the following single variable regression. yi is equal to beta 0 plus beta 1 xi plus epsilon r. Okay. So assume that epsilon I is independently and identically distributed. So with the normal distribution of 0 sigma squared, then show that the estimator beta hat 1 is also normally distributed given the observed xi. So we can assume that so we can express epsilon I, which is normal, as yi minus, we'll call this y hat. And if that's the case, then we can further break down, so yi is normal and then y hat is normal, and we can break down beta hat I into the covariance of xi yi over the variance of xi. And so that is the sum of xi minus x bar times yi divided by the sum of square residuals for xi. And then this can be simplified as sum of c times yi. And so we're just seeing that beta 1 is just the sum of a bunch of random distributions, given that xi is fixed. Alright, so you're just adding up a bunch of normal distributions together. So beta 1 has the sum of normally distributed random variables, which is normal. I'm gonna bring this over here. Okay, yeah, that's pretty good. What does the form mean? What does the form mean in quadratic form? It just means that every term in the variable or the polynomial is quadratic. Terms. So what is quadratic form? What is a simple example how to express in matrix vector notation? So we have something like ax squared plus bxy plus cy squared. So quadratic form just refers to the idea that all of terms in an equation are quadratic, so they're all squared, or they're all multiplied by something, by two different variables. And to express that in matrix vector form, we have x transpose ax. It's exactly equal to a previous thing, so transpose ax. Suppose that y is distributed normally for me and you. Oh, this one is also really hard. Okay. With the known variance sigma, you don't know the value of mu, but you have access to random independent sample size of using n from the sample population. So let y bar denote the sample mean from this random sample. You predict the value of the out of sample y using y bar. Okay, so the mean square prediction out of sample, we have to use this trick here to show that y minus y bar is exactly the same as y minus mu minus y bar minus mu. So That's exactly the same, right? Because you're saying y minus mu minus y bar plus mu, so minus mu plus mu, they just all cancel out. But I think that that actually ends up helping with finding the expectations here. So I think once you do that, you have the expectation of y minus mu minus y hat minus mu. And we square that term. So I think if we square that term, that becomes a pretty nasty polynomial. Let's see. Or we could take the variance of this. So the variance of the term so if we square this term, so we have the expectations here. We have the expectation of y minus u minus y bar minus u squared. So the expectation of y minus u minus y bar minus u times y minus u minus y bar minus u. So do we really have to do this really nasty? Oh, actually, let's see. So distribute the terms here, right? So we have y minus u squared minus y minus u times y bar minus u. And then we add okay, so I think I'm getting somewhere. Y minus y bar times y bar minus u times minus y minus u. Okay, then we add y bar minus u squared. Alright, we're cooking. So this becomes the expectation of y minus u squared minus the expectation of, so 2 times the expectation of y minus u times y hat minus u plus the expectation of y minus y bar minus u squared. So the variance of, so this is equal to the variance of y plus variance of y bar minus 2 times the covariance of y bar. So this should equal to 0 if they're independent. So variance of y, this is just equal to, I think, sigma squared. Okay, so this is just equal to sigma squared. So variance of sigma squared over n. Not too sure why that is. Maybe square root of n. Do we have a slide on that actually? It's just minus 0. I'm curious if we have a slide to show what the variance of the sample mean is. I feel like we don't. Okay, it's a lecture, doesn't really, term review. So y is variance of sample mean equal to sigma squared divided by n. See, so the variance of y hat is equal to the expectation of y hat squared minus the expectation of y hat squared. Oh. Okay, so this actually makes a lot of sense. As the sample size n increases, the variance of the sample mean decreases, indicating that the sample mean becomes a more precise estimator of the population mean, mu. So this property is the basis for many statistical procedures and helps in understanding the distribution. Okay. I actually might need to add this because that shit is important. Alright, browse. So this is all okay. Add. What is the variance of bar x actually, let me see. If x is normal, so sim normal mu sigma squared. So let's see here, the variance of bar x is equal to sigma squared, and then we have n actually, let's copy this. Maybe let's also begin an array end array. All right, and then let's is equal to the variance of the so 1 over n of the sum from I is equal to 1 of to n of xi, right? And so I guess we can show that. So this moves out. We square this term. Variance of so this is equal to n times sigma. So n sigma squared. Okay. Right. So that, and then this is simply equal to sigma and then n squared. Okay. So note that if the yi's are independently identically distributed, so that means they come from the same distribution and picking one does not change the other. So the variance of the sum of random variables is, so variance of some, let's see, so I is equal to 1 to n, variance of bar x xi, which is equal to I see. So we have the sum of variance of xi, variance of xi, which is equal to n c dot sigma squared. Alright, so I'm gonna replace this with xi here. Nice. So variance of the sample mean, if x y does, alright, and then maybe I'll could so why does it make sense for variance? So explain the intuition behind. So variance of the sample mean, so sample mean x is equal to the, so what was it again? So sigma divided by n. I think it's sigma squared, right? So the intuition behind this is that when the sample size n increases, the variance of the, so the variance, so if this sample size is exactly 1, then the variance of our sample mean is exactly equal to the standard deviation. But if it becomes infinity, that means it's 0. Okay. Variance of the standard deviation becomes, the variance of the sample mean, so this is our big term here, sigma squared n, gets smaller and smaller. Eventually, when n is large enough, the sample size n is large enough, the variance of the sample mean, so x is 0. This means that our sample mean is a damn good estimator for the population mean. Except to be precise. Okay, so it seems like the intuition behind this is that the variance of the sample mean is the standard deviation, or the variance of our data set, scaled by 1 over n. So the intuition behind this is that as the sample size n increases, the variance of the sample mean, so that's this big term here, gets smaller and smaller. And eventually, when the sample size n is large enough, so when this goes to infinity, the variance of the sample mean x bar is 0. This means our sample mean is a damn good estimator, exact to be precise, for the population mean. Alright, I'll take that. I think that's pretty good. So that is pretty helpful. Let's keep going. Alright, show that the prediction error y minus y bar has mean 0, and that y and y bar are uncorrelated. So expectation y minus y bar, expectation of y minus expectation of y bar, that's just mu minus mu, that's equal to 0. Y and y are uncorrelated, so I think the covariance of y and y bar, that becomes the expectation of y times y bar minus the expectation of y times the expectation of y bar. The expectation of y and y bar, oh my god, I kind of don't really want to get into it right now, maybe later, but I guess that somehow gets to sigma over n somehow, yeah. Okay, say that's good for now. What does the standard error tell you? It tells you how spread out, or how your means or estimators vary from sample to sample. Some sample data is distributed, I'll take that. Okay, suppose that y is distributed normally, so with mean u, variance sigma squared. You don't know the value of mu, but you have access to a random independent sample size of using n for the same wait a minute. Not entirely sure what this is asking. Oh shit. Wait a minute, I don't want to bury that. Shoot. Okay, nice. I don't think it's buried anymore. Alright. How can we observe the CAPM through the lens of efficient portfolio theory? What is the effect of the market risk premium? Okay, so I'm gonna just try to ask ChatGPT, why is the market risk premium the slope of the capital allocation line? So this is something. Oh, I see. So this is just for the risk of the market portfolio. So the slope then of the cap allocation line is simply just Okay, the Sharpe ratio, it seems like. So slope of capital allocation line Sharpe ratio. Okay, so that actually is very helpful. Okay, I'm gonna write that down and then gotta use the bathroom real quick. So, how can you observe the CAPM through the lens of efficient portfolio theory? What is the effect of the market risk premium? So, CAPM can be thought of as if you were to have a market portfolio represented, so a portfolio of all investable assets, and use that as your efficient frontier. So, the true market portfolio of the CAPM is the tangent portfolio on your efficient frontier with respect to all investable assets. And I think this should have the standard deviation of the market itself. And that represents kind of if you were to have all of your assets invested in a single market portfolio. And the market risk premium in this case is the slope of that capital allocation line. So the slope of that line is defined by the Sharpe ratio. So, and then you're kind of shifting or you're scaling the standard deviation, so the risk of your portfolio by the Sharpe ratio. And that'll give you the returns, and then you just add the risk-free rate. Okay, so I'd say it's pretty good. All right. Let me do portfolio optimization, some portfolio theory this year. All right. What is the slope of the capital market line? So the slope of the capital market line is the Sharpe ratio of the tangent portfolio. So this is the expected return. So let's do math. B. So expected return of the R plus tangent minus the risk-free rates, and then we want to divide this by the standard deviation of our tangent portfolio. Okay. This Sharpe ratio scales the standard deviation of our degree of risk. Okay, so Sharpe ratio represents the extra term for taking on one more units of standard of risk, where the risk is represented as the standard deviation. Okay, so the Sharpe ratio represents the extra return for taking on one more unit of risk. So your risk is represented as the standard deviation. How does this relate to the CAPM. So in terms of the CAPM, the market risk premium plays a role in determining the slope of the capital market line. In this case, the slope. So in terms of the CAPM, the market risk premium plays a role in determining the slope of the capital market line. In this case, the slope becomes, so we have the expectation of our market minus the sigma squared of the market. Okay. So we have sigma squared of the market portfolio. Oh, right. We don't want the sigma squared, so that's variance. Just want sigma, which is standard deviation. Okay. The numerator is precisely the market risk premium. Okay. So what is the equation for the capital market line? So this is return is equal to, say, RF plus, so sharp, we have math BB of our change portfolio, then we minus the risk-free rate, and then we divide by the sigma of our tangent portfolio. So sigma of our tangent, RT, and this is I'll call this RP, sigma RP. Right, so I think these two sigmas are different. One is for the portfolio, one is for, math BB. So I guess that is one big thing. So the capital market line is a measure of the expected returns of a portfolio that combines the risk-free assets and the tangent portfolio. So the slope of the capital market line is the Sharpe ratio of the tangent portfolio. Okay. Yeah, so I think that's pretty good actually. Going to continue our Let's continue. Okay. Suppose you want to construct a portfolio of two stocks, X and Y. The returns of two stocks are normally distributed. X is Okay, 0.1, 0.1, y, 0.2, 0.2, correlation xy 2.4. Expected return on minimum variance portfolio. So I don't think I actually did all of the math for this, but all we need to do is find the derivative of the variance and set that equal to 0. So we can minimize the variance itself, and then when we're taking the derivative, we need to take that with respect to w. So we have to minimize the variance by changing w. The variance here is a bit complicated because we're going to do variance of x plus y, and so the variance of x plus y is, I believe, w squared times variance of x, and then we add 1 minus w squared times variance of y plus 2 times the covariance of x and y, and we're given the correlation here. So I think we're going to have to do 2 times, actually w times 1 minus w, and then the correlation between x and y, and then we have to multiply that by the standard deviations of x and y. So the square root of the variance. Yeah, that's rough. Okay, so show that the mean squared prediction out of sample error is equal to sigma squared plus sigma squared divided by n. Oh my god. Alright, so I have to see real quick when our office hours is, but let's get through this one real quick. Okay, so sample mean prediction out of sample error. We have to show that expectation of y minus y bar squared is equal to sigma squared plus sigma over n. So you don't know the value of mu, but you have access to a random independent sample size, and for the same population, sample mean from this random sample. Alright, so you can do some fancy tricks here. First, by re-expressing this as y minus mu minus y bar minus mu, and then you square those terms, so you kind of distribute them out, and then you multiply them together, so you distribute them. It'll be y minus y bar squared, and it'll be y minus mu minus y bar minus mu squared. So it'll be y minus mu minus y bar minus mu times y minus mu times y bar minus y bar minus mu. So we take y minus mu squared minus 2 times y minus mu times y bar minus mu, which is 2 times the covariance, and then we add the add y bar minus mu squared. So there's 3 different terms here. One is the variance of y, one is the variance of y bar, and then one is the variance of the covariance of y and y bar. So that becomes 0 because y and y bar are uncorrelated with each other, so they're independent, and I believe y itself is the variance of y is just sigma squared, and then the variance of y bar, so our sample mean, is sigma squared over n. Right. So we just add those 2 terms together. Yes, sir. Yes, sir. Determinant matrix. You can kind of think of it as the factor which we scale the area of the matrix. Okay. Yeah, I will need to come back. Okay, so let's see here. To consider the sample regression. Actually, before I do that, let me see when office hours are. Oh man, I can see my 51 out of 120 staring right back at me. 12:32. All right. Yeah, tune in. See, I'm gonna text my friend real quick. See if they're joining. Minutes. Alright, so with that being said, simple regression without intercept yi is equal to beta xi plus epsilon. Suppose n is equal to 1, y1 is equal to 2, and x1 is equal to 1. So what is the value of beta OLS? I think in this case, beta OLS is going to be minimizing the sum of squared residuals. In this case, it should be pretty simple. So y1 is 2, x1 is equal to 1, and we only have one observation. So I think it'll just be 2. So 2 times 1 is 2, and then 2 is exactly equal to 2. Okay, yeah, that's good. So consider a default free zero coupon bond paying $1,000 in 1 year. Assume that the risk-free interest rate is 5% annually compounding and the financial market is well functioning. So what is the price you are willing to pay for the bond? Case A, suppose that the bond is traded for a price of $9.40. Is this an arbitrage opportunity? If so, how can you profit from this? How can you profit in this situation? So, and then case B, suppose that the bond is traded for a price of $9.60. Is this an arbitrage opportunity? If so, how can you profit in this situation? So the bond traded for a price of $9.40. So these are both arbitrage opportunities because they differ from the price we're willing to pay for the bond. I kind of remember this question, but I think the intuition here is that, okay, you have $1,000 in 1 year. You can discount at 1.05%, this $1,000 right here. So you get the present value of the bond, it's around $9.50. Now suppose that the bond is traded for a price of $9.40. So that means it's cheaper than what you're currently paying today, or the intrinsic value of the bond. And so what you could do then is, I think you could take out a loan at 5%, use that loan to buy this bond at 940, immediately pocket the difference. Okay, so you take out, $950 loan, so the price of the bond, and yeah, I'm just thinking in my head, wow, 5%, 1 year, that's like $50. That's actually not too bad. But basically, you take out $950 from the bank, or the price of the bond, the intrinsic value of the bond, and hopefully you'll get it at 5%. It only works if you get it at 5%. And you use that to buy the bond immediately at 940, and you can pocket the difference between the two. And when it comes to paying back the loan in 1 year, then you just take the maturity of $1,000 and you pay off the $1,000 interest plus principal for that loan. Alright, case B. Suppose that the bond is traded for a price of $960. Is this an arbitrage opportunity? If so, how can you profit in this situation? So the bond is traded price of $960. It's higher than what you would normally pay for it, so you could short sell it. You could short sell it and then put the money in a bank to put whatever the bond is worth today in the bank, and hopefully collect 5% interest. That'll accrue, and you can pay back. You can buy the bond back at maturity and then just pay the $1,000, and you immediately pocket the difference between them. But yeah, 1 year needs to pay back $1,000 on a loan, which you can pay back using the bond when it matures. Okay. So case B, bond short sell deposit in cash. What's your rate? Realize deposit leftover cash. Okay. Yeah, I think it's pretty good. Ooh, so what is the value of beta ridge? So in the same exact problem, ensure that has shrinkage effect from the OLS estimate. The thing we could show then is, so beta ridge, I believe, is equal to the argmin. So in this case, we're trying to minimize the same function. So you're trying to minimize epsilon, right? Epsilon is yi minus beta I. In this case, beta is beta ridge, but you also add the kind of penalty term, so that's lambda times the sum of all betas. So the more, I guess you could say, betas that you have, the more, or positive betas, I think the lower the value of those betas would be. So that means that we're trying to minimize this function that depends on lambda, and we have beta ridge. So I think we might have two different variables here, not a single analytical solution where it goes down to a number like the beta OLS. But let's try to think this through. So same idea, we have 2 minus beta ridge times xi squared. So we square that term, and then we add, in this case, just lambda beta I, or beta ridge. And if we square that term, so that becomes so y minus beta ridge would be 2 minus beta ridge squared so it would be 4 minus 2 beta ridge plus beta ridge squared, right? And then plus lambda beta ridge squared. So we also square that too. And then could maybe move the -4, or we can subtract -4, so that becomes -4 on one side, and we're just left with minus 2 beta ridge times beta. Okay, yeah. Having a hard time visualize this in my head, so let's do this. So we have this beta ridge 2 minus beta ridge, and then this is equal to, well, plus lambda, and then we have beta ridge squared. So this is equal to 0. Oh, not yet. Oh, right, so augment. We can minimize that function, so instead of expanding it out, we could just do 2 times -2 times 2 minus lambda beta ridge. Right, and then we add 2 lambda beta ridge, so that's equal to 0. So we just divide by 2. Divided by 2, we have -2 plus beta ridge plus lambda beta 2 is equal to 0. So this becomes beta ridge plus lambda beta squared is equal to 0, is equal to 2. And then we just take out beta ridge times 1 plus lambda, and that's equal to 2. Beta ridge is equal to 2 over 1 minus 1 plus lambda. Okay, so in order to find the beta ridge, we have to actually minimize the function, right? I totally forgot about that. So we have to minimize this function with respect to beta ridge. So it'll be 2 minus beta ridge squared plus lambda beta ridge squared. To find the argument with respect to beta, that becomes -2 times 2 minus beta ridge plus 2 times lambda beta, and that's equal to 0. So we set that equal to 0 to minimize the function. Then we could just divide by 2, so -2 becomes -1, and then just 2 becomes just 1, and 0 divided by 2 is just 0. So then we're left with -2 minus beta plus lambda beta. And we distribute the negative, so it's negative 2 plus beta plus lambda beta, that's equal to 0. We add the 2, and then take out the beta, so it's just beta times 1 plus lambda is equal to 2 divided by 1 plus lambda, then beta is equal to 1 over 2 over 1 plus lambda. So this has a shrinkage effect because as you increase lambda, so 2 was the exact same thing as the previous OLS beta, but we shrink it by lambda. So if lambda is greater than 0, that means that our beta 1 or our beta ridge value is going to be less than the OLS parameter or the OLS estimate. I see, yeah. This is where I got it wrong, because I was wondering if I did something wrong yesterday. So this just becomes negative, so negative 1, negative 2 plus, yeah, we don't need this beta here. We don't need this beta either. So it'll be 1 plus. We don't need this one either. Right? We just divide by 2 both terms. Okay. Alright. Let's go. Alright. So I think that's pretty good. Alright, so this, we have variance of x, variance y, variance of sample mean. U-trick. I don't want to get too deep into it because I'm going to hit at some buzzer beaters. Basic proof, linear expectations. So iterated expectations. This is going to take a little bit, so I'm just going to say it's good for now. This one, I don't even know. It uses some weird Lagrangian thing. I don't know if I really want to deal with this right now. I'll just say it's good for now. What is the expected return of volatility of the portfolio? 50% invested in stock X, 50% is in Y. Alright, so expectation of X plus Y, I think it's 0.5X plus 0.5Y, so that's just going to be weight 1.1, so 0.5 times 0.1 plus 0.5 times 0.2. Expected return. Volatility, it's a bit harder, so I think we need to do, in this case, 0.5 squared times 0.5 squared times 0.1 plus 0.5 squared times 0.2 plus, so this is the covariance term, in this case is correlation, so we need to do 2 times 0.5 squared times correlation times the standard deviation of x and y, so I believe that's the square root of 0.1 and 0.2. Yeah, that's good. That's good. Slope of the capital market line, how does it relate to the cap M? So the slope of the capital market line is the Sharpe ratio of the tangent portfolio. So it's expected return of the tangent portfolio minus the risk-free rate. Then we just divide that by the standard deviation of the returns for the tangent portfolio. And this relates to the cap M because the numerator of the tangent portfolio, when we're looking at all of the investable assets, in, I guess, the entire universe. So that's actually the market risk premium. That's your expected return on the market portfolio minus the risk-free rate, and then we divide that by the standard deviation of the market portfolio. So the risk-free rates, the market risk premium here is super important whenever we're looking at the capital market line. Okay. So I have about 4 minutes. I think I'm gonna take a break real quick and then just come back to this. Maybe after the meeting, I might start on 472, my deep learning class. So thanks for tuning in, and had a pretty good study session. My mind's kind of getting in overdrive. I think the coffee's starting to get to me a little bit, but yeah, I'll see you guys in the next one. Peace. Peace.